All right, good morning, everyone. It's Friday, 9/11, and hopefully a lot of you guys, if you're not getting to watch this broadcast live, you'll get to watch the recording. I do want to go over a schedule real quick moving forward, and I posted this on Moodle, but Monday we will have a test review, and we'll go over your Chapter 2 homework, and then Monday in lab, we will actually be testing concrete. So I want you to participate as many as possible. So, don't wear real good clothes because there's a possibility you'll get a little bit of concrete on you. And then also at lab time, the first formal lab report is due. And then Wednesday, we'll have our first test. So that's what we look like going forward the next few days. All right, I'm going to share the screen. We'll get back into notes. We started our notes on concrete. I posted a short video about the making of Portland cement. If you get a chance to watch that, would be good. And let's see. So I think here's where we were. We were talking about the actual physical size of Portland cement grains, if you would, and how that affects some of the properties. And so there we go. Hold on a second. All right, so here's a good definition. This will be a good test question. Hydration. It is the chemical reaction that takes place when Portland cement and water are mixed, and that's what actually causes the concrete to set and get hard. And then after that point, after the chemical reaction takes place, it doesn't matter if it gets wet. It's not going to, reconstitute into its original constituents, but we have something new. So, the hydration process causes the cement and water to bond and adhere to the aggregates that we're using, typically gravel and sand. So pretty important concept, hydration. So it's a good test question. Make sure you mark that. It's considered complete after 28 days. I'm going to show you some curves in just a second. They're in the notes and in your book. But it can continue to gain strength well after that, depending on how much moisture is actually available. And that's why in the lab, when we actually make laboratory test cylinders, or even on a job site, when you make test cylinders to test the strength of concrete, we actually take those after 24 hours. We strip them out of the mold, so they're set and hard, and we place them in a water bath in a lab or in some type of laboratory setting. And then they sit there typically for 7 days, and we test at least one. And then the rest of them we test after 28 days, which most, I won't say all, but most specifications are written based on 28-day strength of concrete. So that's why that's kind of important. Back to hydration, since it is a chemical process, something is happening with, some heat generation. And if you are around concrete when you are placing it, so remember, fresh concrete, green concrete, or plastic concrete, those are all synonymous. You can actually feel just a little bit of heat that's coming off of those. It just depends on how much, the volume of concrete that you're dealing with. We'll talk about that in just a little bit, maybe some impacts as to what type of cement that you might use. So figures 4.2 and 4.3, I'm going to throw these up in just a second, but they're actually in your book on page 93, that hydration is related to the strength and how much. So here's the figure 4.2 looks like out of your book there. And what you can see is if we can what's called moist cure, so that would be all the moisture that it would need. So water bath obviously would take care of that. The strength will continue to increase. The other, as you can see, it kind of shows a slight drop off, but basically would be negligible. And to the right here on that side, we also see compressive strength and percent of a 28-day moist cured concrete. So don't let that confuse you. That just means that those curves are based on moist cure the entire time. So at 28 days, you would come up and see that would be exactly 100. Now where we will use this figure here is when we test concrete at sometimes even 1 day, but usually 7 days, 3 days, 7 days. If you're wanting to know, and it's just an estimate really, what would be the strength of my concrete at 28 days, which is what the specification would be written for, but I'm testing it at 7 days. So you would use a chart like this and come up and you might say, hey, it's going to be, 60-some% or 70% or even 75%, something like that. So that would give you an idea of what your strength would be. So if we would take, let's just say, I'm using a calculator, we would take a strength of 2,000 PSI, and we are going to assume that that's at 7 days, and we're going to assume that that's, say, 65% of the strength. We would divide the 2,000 by 0.65, and we would estimate that the strength would be 3077, something like that. I'm going to show you that real quick. I'll write that in. So that would be, let's just say if we had a F prime C 7-day test. And let's just go ahead and go over that just to make up some numbers. Let's just say we had a test that's 60,000 pounds. And so this would be, the strength would be just like we saw before, stress is equal to, or strength P over A. And let's just say that A in this example is a cylinder, so it's pi d squared by 4. And if I let B, since I know a 6-inch cylinder, I'm going to say that the 6-inch cylinder is going to give you an area of 28.27 inches squared. Okay, so if we say 60,000 divided by 28.27 inches squared, let's see what we get there. So I'm going to get a strength of 21, I'll just say 2122 PSI, pounds per square inch. All right. Now, once again, if we just assume based on the figure 4.2 that's in your book, that at 7 days, we're at 65% of the 28-day strength. Okay. So then we would say, okay, then what would the estimate be? So we estimate the F prime C 28-day would be equal to the 7-day strength, 2122 PSI, divided by the 65% as a decimal. And if we did that, we would get 3265. And that's PSI. So that's kind of how that process would work. All right, any questions on that? Okay. All right, so this figure here is also out of your book. This is on page 94. And this goes back to those types of cement that we looked at. So I jumped ahead 2 slides here just a little bit. We talked about this on Wednesday. So you can actually buy different types of cement, and some of them are just chemically slightly different, and there's a slide earlier that shows that. And then some of them, like ASTM type 3, which is called high early, are just smaller cement grains. So remember, the example was like, if you have, you go to get ice out of your refrigerator, and you have cube and crush, and you want your water to cool as fast as it possibly can, then you're actually going to push crush because there's more surface area for the water to come in contact with. So it's going to cool faster. So the same thing can be said about the hydration process. If we have smaller cement grains, then the water can come in contact with those cement grains, more of those cement grains, because of the higher surface area. And so therefore the hydration process will take place faster, and the strength will be gained faster, and it will set faster. So now in long term, there's not going to be any difference, but that's why they call it high early strength. And so I mentioned like Eastern Vault and places like that, they actually use for their products, they use type 3. And it's not really because they need the high strength directly as far as a load application, but what they want to do is they want to be able to come in the next day and strip their, the product out of their molds, clean the molds, and do it all again. And if they were using normal, like type 1 cement, then they wouldn't be able to do that. So it's important for them to gain enough strength for them to be able to, restart the process and cast another set of whatever, whether it be vaults or steps or manholes or whatever they're doing. A couple other interesting ones here might be low heat. So, I mentioned earlier that hydration is a chemical process and it emits heat. It's generally not a problem, but, if you had something like, and I'll be kind of ridiculous, but Hoover Dam or something that you have a tremendous amount of concrete, then it probably would be important for you to control the heat. So those types of mass concrete, you might pick a type 4. I've not much experience with a type 5, but I guess if you had something in the soil that would react with the concrete, sulfate resisting type, so something that's going to be detrimental to the life or longevity of the concrete, then you would use that. Now, I did mention that most, when you buy Portland cement at Lowe's or somewhere like that in a bag, it's 94 pounds. It's actually, what I've seen is type 1/2A. So what that means is it actually meets the specifications for criteria for ASTM type 1 and type 2, and it has air entrainment. So that's the air entrained Portland cement. So type 1/2A is typically what you would buy. That would be your normal or typical bag of Portland cement. Now, remember not to be confused with an 80-pound bag of Quikrete that you can buy, because that's already got all the aggregates in it. So we're just talking about Portland cement. Portland cement is to concrete as flour is to a cake. So you can remember it that way. All right, now I'm going to jump back to this hydration. So concrete, once again, it does not dry. It sets and hardens. And so that typically takes 3 to 7 hours. We'll talk about some admixtures later. We can control that a little bit. And obviously, like the high early strength cement would alter that some, but just for your typical mix, traditional mix, 3 to 7 hours. So it doesn't really matter if you're placing, 1 yard of concrete, if you're paying for that, or if you're placing, 50 yards of concrete. It's still going to take most of the day for, a contractor or whoever's working that concrete to, to the finished product, because it takes so long for it to set and for them to be able to work or finish it. And we'll talk about concrete construction next week or sometime. All right. Next slide, mixing water. So this is potable. Some people say potable water. And basically this is just a good rule for concrete that if it's safe to drink, it's safe for concrete. Most of the time it's not a problem, but if you do have impurities in your water, it can affect, like the notes say, setting time, or it could cause efflorescence. Is kind of like a chemical reaction that's taking place between the cement and the water. Sometimes you even see it in mortar, like on a masonry wall. And it causes, it's less of a structural issue and more of aesthetics, but it causes like most of that I've seen is a white substance that forms on the outside of the wall. So, you know, that might go along with kind of a discoloration. So reinforcement of, corrosion of the reinforcement would be a much more serious problem. That would be a structural problem. So it's best to use potable water for your concrete. And if it's a problem, you can do comparative tests, or if you think it's a problem, to see what effects that the water might have. As far as the amount of water and any type of adjustments, and we'll talk about this a little bit in the lab, stockpiles are generally kept outside. So when we do, and we'll do this on Monday, when we do a concrete mix design, we assume that the aggregates are at saturated surface dry. Now we kind of know what that is based on the notes in chapter 2. If you have aggregates that are really dry, like sometimes that happens to me in the lab, and it will happen to us if I have sand or gravel that's been sitting in the lab, it can actually absorb more water out of the concrete than it's supposed to. So it actually takes from the cement particles, and that's not a good thing. So we have to add a little extra water. On the opposite side of that, if you have a stockpile outside and it's been wet and the aggregates are very wet, then that can put too much water in your concrete mix, and so you might have to adjust for that. All right, any questions on that? Good. Okay. The next slide is about reinforcement, and I think most folk are used to the word or have heard the word rebar, and in the past, you know, this was typically steel. There are different grades or strengths of rebar that you can get, and there are different sizes, and we'll talk more about that actually later on in the semester when we cover steel production and steel products. It's added to concrete because concrete is strong in compression and weak in tension. I think in class Wednesday we had a little beam that I drew out for you and showed you positive bending. So it wants to sag in the middle. So the upper fibers are in compression, they're fine. But the lower or bottom fibers are in tension. So it just in that scenario, if that's the only load condition that we had and we just had positive bending, we would want to put the rebar or the reinforcement in the bottom of that beam. Now, there are other things that have been developed in the last several years. They've really not caught on like rebar is still your predominant reinforcement. But there are fibers, so, you know, kind of a geosynthetic product, and they are just, looks like, you know, geosynthetic or synthetic hairs or something, you know, it looks kind of weird, and sometimes you can see it on the surface of the concrete, but it does kind of the same thing. When the concrete goes in tension, the strength of all these fibers, you know, there's, let's say, thousands of them in there, will help to resist that. There are also fiber composite rebar, and so sometimes you'll see this as green. Now, they also make coatings for rebar, and I could show you all that if I can remember next week in class. That's for corrosion resistance, but this is actually a non-steel product, so it's a true fiber composite reinforcement. All right, and then I think there's a picture here of a pretty dense rebar mat. It looks like on a bridge, and you can see the parapet wall and how all that's going to mesh together. As far as the aggregates go, most of those properties that we discussed in chapter 2, strength, durability, abrasion resistance, you know, those kind of things are going to be important as an aggregate that we use in concrete. You know, most of the time we think of gravel and sand, and when we mix those as our aggregate, we estimate generally that reinforced concrete is going to weigh about 150 pounds per cubic foot, but it could range slightly depending on what kind of aggregates you use. and I think I mentioned this before, so we can actually use an expanded shell or something like a vermiculite, a perlite, should be a comma, um, zonalite, any of those would be lightweight aggregates. And so if we mix those instead of the gravel and the sand, or at least a portion, we can get down to even as far as 15 pounds per cubic foot. We can use what's called glass beads. We can use little styrofoam beads, and all of those can get down below the unit weight of water. And so actually a block of, let me say, concrete, it's not traditional concrete, looks more just like a mortar, but it can actually float. And then on the other side of that, if we need something that would be really heavy, like a counterbalance on something, a counterweight, we can actually put like lead shot or some type of steel shot that weighs like 490 pounds per cubic foot to get our concrete unit weight up to maybe as much as 400. So those are the different aggregates. We don't use those very often, but every now and then you'll see a special application there. As far as the water goes, kind of the same thing goes. I've seen some very strong and durable mixes that have small stone, like a pea gravel size stone in it. I know VDOT is using that. Typically, the smaller aggregate takes a little more water and less water for the larger aggregates. But we'll go over. I don't want to do that today, but we'll go over next week the maximum aggregate sizes within a member by code. So we'll talk about ACI 211.1. We'll come back to that, and I'll do some examples on the board for everybody. That's something I'd rather do in class, so we'll talk about that. All right, let's go over some admixtures. So anything besides the cement, the water, and the aggregates that we put into concrete would be considered an admixture. And there's really a couple ways, you can make mixed design modifications, which would be how much cement, how much water, how much sand, how much gravel. And you can kind of get a different product. And I know we even talked about fly ash, which is actually an admixture. So there's several things that we can do. But, over the past probably 20 or 30 years, they've come up with some really good admixtures to control, or to create a desired effect, you might say, or maybe adjust the setting time or things like that work really well. And there's on page 98 in your text, there's a whole list, and I'm not going to go over all those, but I will go over. I'm sorry, it was the wrong page. It's page 102. So there's a whole list of those that show common admixtures and their functions. Yeah, it's on page 102 in your book. So for an example, I'm going to pull my text over here. I'll just go over a couple of these that I think are the most common type of admixtures. So accelerators. And the desired effect is accelerate setting and early strength development. So as opposed to using type 3 cement, we can just place accelerators, which generally these just come in a gallon jug or something like that, or they probably have them at the batch plant in 55-gallon drums, the very common ones. But they'll just bring those, and after the truck arrives on the job site, they'll just kind of pour the right amount in for the amount of concrete that they have. And work it that way, and that's probably more cost effective than using like a high early strength cement. But anyway, why would they do this? Well, if they need early strength development, or if they need to speed up the set time. So why would they do that? Well, maybe they need to finish the concrete faster. So in order for them to be able to actually place a load, depending on what kind of finish they have, they might put some accelerator in there. And then I'm going to skip way down to, should be decelerator or retarder. Yeah, retarders are on the top of page 103, would be the opposite. So if you had a whole lot of concrete to finish and you only had, a few laborers, it may be a problem that you wouldn't be able to finish all the concrete in time. So maybe in part of it, you would put a retarder in. And so that would actually delay the setting time and enable, your crew to finish the first part and then get over to the second part, something like that. We already talked about, I think another common one would be air entrainment. And this can be done one of two ways. It could either be done with the cement, which would be, once again, like type 1,2A, or it can be done just as an admixture, once again, after the concrete is mixed. I didn't really tell you why we need this, though. So air entrainment, it's not air gaps or voids that you could see with your naked eye. We don't want those. We don't want void spaces in the concrete. But these are, let me say, microscopic air. So, but it's still there. It's just really, really small. And what it does is it actually allows the concrete to expand slightly under freeze-thaw cycles. So when it freezes concrete, everything generally, most things expand that I know of when they freeze. And so it allows that to happen without causing enough stress on the concrete that would cause it to crack. So it's very important. Any type of environment that's going to experience freeze-thaw, you would want air entrainment. Now, when would you not want air entrainment? Well, generally for an interior floor slab or something like that, you probably wouldn't want air entrainment. But for most of the time, for foundations, or let's just say for sidewalks or something that's going to be outside in our area, absolutely, you're going to have air entrainment in there. So, and you can use multiple admixtures in the same mix. So it could be, you could have air entrainment and accelerator in the same mix. The next one that you may run across is are permeability reducers. So if you have concrete that you do not want water to be able to flow through, and generally that we don't want water to flow through, but over time, water can make its way through concrete. So that would be something that we'd put in there to decrease that permeability. I see one here called pumping aids. So there's a lot of applications where we can't back the truck up to where we're wanting to place concrete. So let's just say, for instance, that we have to place a floor slab or a beam or something on a 5th story, hotel, something like that. Then what they do is they pump that. So you can Google that and watch them. It's a pretty neat process. But in order for them to pump concrete, it has to be of a certain consistency. So, think about it, instead of thinking about it something really thick, think about it something more soupy, that they're able to actually run through the pump. But at the same time, it's not going to cause any segregation of your aggregate. So those are pretty neat. Really, besides pumping agent, I think the one that's much more common with pumping concrete that I've been around are called superplasticizers. So a superplasticizer will increase the flowability of the concrete. And I'll talk about the water cement ratio later, but so it enables them to pump it or work the concrete. So they don't have to even use it for pumping. If you had a very dense rebar mat that you would have difficulty getting the concrete into all the void spaces around all the rebar, then typically they would use a superplasticizer to help that concrete flow without segregation again. We're going to talk about a test either today or in the coming lectures that it's called a slump test. And basically you put concrete into a cone, and then you're going to lift the metal cone and the concrete's going to slump down. Well, a traditional concrete mix, may slump 3 inches or 4 inches or something like that. But when we have superplasticizer in there, it actually the same mix may slump 10 inches. So it really causes the concrete to flow. So that's a pretty common one. And the last one I see, once again, are water reducers. And I think this is probably the next slide. So I'll go ahead and put this up. But so what we have when we talk about a water cement ratio, that's the weight of water over the weight of cement. And as the water cement ratio goes up, the strength goes down. So in other words, the more water that we place in a concrete mix, everything else being the same, the strength is going to decrease. And the less water we can put in, the more the strength is going to increase. So, you know, if you think back to something I said earlier, that concrete needs all the moisture it can get, okay, in order to cure properly and to gain that strength. But this is actually the mixing water. If we put too much water in, what the water is going to do is actually replace something else. It's going to replace an aggregate or some cement, something that we don't want it to replace. So it's a very delicate balance there. We like to keep the water cement ratio as low as possible. Typical water cement ranges from about 0.35 to 0.6. And according to your book there, the last note on that slide, a 0.01 drop in a water cement ratio equals about 100 PSI increase in 28-day strength. So definitely the water cement ratio makes a difference. Now, I want to go over that calculation real quick because it's something that we're going to use when we do our proportioning of our concrete mixes. So I'm going to pull this back up and clear that out. Can you see that okay? Whiteboard? Okay, good. All right, so if we have, so the question might be something like this. It might be given a water cement ratio of, I'll make it easy and say 0.5. And then, so I want to show you this it's really just a conversion, but find the number of gallons per bag of Portland cement, okay? That's pretty sloppy, but we'll go with it. All right, so we would start off, I'm gonna do this just like I would a conversion. So I'm gonna start off with 0.50, all right? And that is actually, let me see something here. So remember, water cement ratio is the weight of water. So we could just make this pounds of water over 1 pound of Portland cement. And let's see if that makes sense there. So that's a water cement ratio of 0.5. So that's pounds of water over pounds of Portland cement. It could be grams over grams, whatever it is. Doesn't matter as long as your units are the same here. All right, then let's see what we know here. So we've got 94 pounds of Portland cement in 1 bag of Portland cement. Okay, and that's going to enable me to cancel this. And then I know that there are, and if you don't know this, commit it to memory, 8.34 pounds of water in 1 gallon of water. All right, so that'll let me cancel this. And then when I do this, so that's going to give me gallons of water per bag of Portland cement. So the way that I would do this would be 0.5, everything across the top I'm going to multiply, times 94 times 1, divided by everything that's on the bottom, divided by 1, divided by 1, and divided by 8.34. So that's going to give me I'll just say 5.6 gallons per bag. 5.6 gallons of water per bag of Portland cement. That's kind of how that works. Now let's do one just the opposite, and you'll see it just really flips over. So this time we'll say, okay, so given, let's say 6 gallons of water per bag of Portland cement, find the water cement ratio, okay? So we'll do this in just the opposite. So 6 gallons of water per 1 bag of Portland cement. Now, we want to be able to cancel, so we say 1 bag of Portland cement is 94 pounds. So that cancels that. and 1 gallon of water, H2O, is 8.34 pounds. All right, so this one is just going to be 6 times 8.34 divided by 94. So this one's going to be a water cement ratio of 0.53. Okay, that's the answer. All right, you got any questions on that? You good? Thumbs up? Very good. All right, so that's how we go back and forth between water cement ratio to gallons per bag and gallons per bag to a water cement ratio. Okay, and that's probably a good place to stop today. So we'll be able to pick up on Monday. We'll have a test review, but we'll be able to pick up right there and go into our mixed design process. So any questions on anything?
Did we skip chapter 3?
Yes, we did.
Okay.
So
Sure.
the first test is on 1 and 2, and
Okay.
then the next test is actually just on 4, just on concrete, and then we'll go back to chapter 3.
Okay, and I'm sorry, I missed it. You said we'll review on Monday, and then the test is when? Wednesday?
Wednesday, yeah. So we'll work something out there.
Okay.
All right. So
All right.
I hope everybody has a good weekend. Go Ears.
All
Take care.
right. See you. Thank you.